This is going to be our third example of finding the volume of a solid of revolution. This time, though, we're going to go about the y-axis. So we're going to take this region that's bounded by the line y equals 0.5x plus 5, or you can think of this as negative 1/2 x plus 5 if you're more of a fraction person versus a decimal person. And we're going to rotate this around the y-axis this time. So if you want to get an idea of what this would look like, I'm going to zoom this up. So this curve is, I don't know what that looks like to you. Looks like a snow cone cup that's sort of squished down, a little flattened out snow cone cup. And we're going to slice it with discs, but this time we're going to do it horizontally. Here's the picture of what it looks like, or what the process we use looks like. I will tell you to note that this time the thickness is a little change in y this time. So if we're going to use dy as our thickness, that sort of dictates that we need to use y as our variable. We need to get the function in terms of y, and also our limits of integration need to be in terms of y as well. I'm pretty sure Professor Mizell is going to tell you all this in a few minutes, and at this point I'll turn it over to him.
All right, so let's do some examples revolving around the y-axis. First, let's do a disk revolving around the y-axis. If you're using the disk and washer approach, when you're revolving around the y-axis, you have to integrate dy, which means you need the function in terms of y. So the region we're looking at is the straight line y equals negative 0.5x plus 5. That's y equals negative 1/2 x plus 5. From 0 to 10, well, if you plug 0 in here, you get 5, so it goes through the point 0.5. And if you plug 10 in here, you get 0, so it goes through the point 10.0. And notice this region does completely touch the y-axis. As long as the region you're looking at touches the axis you're revolving around, you can use the disk method. But again, we need this not as y equals f of x. We need this as x equals f of y. So I need to solve negative 1/2 x plus 5 for x. But that's easy to do. Just subtract 5 from both sides. And then multiply both sides by negative 2. Here, I'll get negative 2y plus 10. Here, negative times negative is positive. 2 times 1/2 is 1. So in terms of y, this straight line is x equals negative 2y plus 10. That is, this line is y equals negative 0.5x plus 5, or x equals negative 2y plus 10. One other thing, since we're integrating dy, our limits have to be the limits on the y-axis, not the x-axis. X goes from 0 to 10, but y goes from 0 to 5. So the correct integral to find this volume is pi times the integral from 0 to 5 of f of y negative 2y plus 10 squared dy. This is awfully close to something raised to a power sitting next to its derivative. The derivative of negative 2y plus 10 in terms of y would be negative 2. I can fix that by multiplying by negative 2 on the inside and dividing by negative 2 on the outside. I now have something raised to a power. This whole thing here, negative 2 dy, is my du. So minus pi over 2 stays on the outside. But this will just integrate as negative 2y plus 10 cubed over 3, where now I have to plug in 0 and 5. So let's leave negative pi over 2 for now on the outside. If you plug 5 in, you're going to get 0. minus, if you plug 0 in, you're going to get 10 cubed over 3. That's 1,000 over 3. So negative times negative is positive. That's good because the region is in the first quadrant, so the volume should certainly be positive. And 2 goes into 1,000 500 times. So the volume of this region revolved this time around the y-axis is just 500 pi over 3.